Well, hello to you all and welcome to this mathematics skills in Year 12 chemistry session that is being run by Carlam Cymru. So as you can see there, it is primarily aimed at trying to target and support you with your development of those all essential mathematical skills. Now, so for those of you that don't recognise me, my name is Nera Stevens and I'm a chemistry teacher in Bro Pedyr in Lampeter, West Wales, but more importantly, I'm also an examiner for the WJC. So hopefully that will give me a bit of an edge to help you and guide you in the right direction when it comes to the mathematical content that will be required from you during year 12. So mathematical skills, as it reads there for you, it does crop up awfully often in GCE chemistry. So the weighing of the assessment is that it has to be at least 20% mathematical skills being assessed and questioned. But if I was being honest with you, it is probably nearer to about 30% when it comes to reality, especially when it comes to that unit 1. In AS chemistry because of that massive content that is covered in topic 1.1 1.3, which obviously, as the title of 1.3 suggests, being chemical calculations, it is quite heavy in that mathematical content and what the requirements are. So for that reason, it is very, very important that you feel comfortable in being able to answer these mathematical questions. Side by side with the fact that they recognise that it is quite a heavy component, especially in Unit 1, the exam board WJC have in fact prepared quite an useful resource for you. You may not know it exists, okay? So I will guide you to where to find it, but more importantly, I've got a direct link that you can use as well. So the aid itself is designed to kind of help you master the mathematical skills that are required throughout AS and A2 chemistry. And hopefully it will then help you kind of get your head around how to do certain things, how to apply it to different situations. And the guide itself has been split into 5 sections. So it starts off with that chemical calculations requirement. So it then leads on to being the equations and how to balance them, taking into consideration stoichiometric ratios, etc. Rearranging equations. I cover this quite heavily in this session that is about to run, because it is one of those kind of pitfalls that a majority of pupils do fall into if they aren't kind of confident in applying certain skills. Changing units, another sort of pitfall that pupils tend to fall into. And then obviously at the end of that guide that they prepared for you, there is an opportunity then to put it into practice, which is obviously the best way of getting your head around certain things as well. So you will have access to this PowerPoint once you've watched this session. And there is that link there for you to just directly click onto, and then hopefully that will lead you to the aid, so that you don't have to go hunting for it yourself if that is not what you want to do. So just to get kind of a springboard task, a starter, as your teachers may call them in certain schools, and you're welcome to pause it and attempt these independently, because I will be rushing through this springboard task quite quickly. But if you want to stop and attempt it yourself, then by all means, it'll probably do you some good. So it's going to base it around these 2 kind of core principles, was that you picked up in GCSE chemistry, of course, that the number of moles of any substance is equal to its mass divided by the molar mass, or if you're talking about an element, obviously we're talking about its relative atomic mass, AR. And then, even though it wasn't studied in any sort of great depth, if I was honest, at GCSE, you were introduced to this Avogadro's constant, which is the number of atoms or molecules that are present in a mole of a substance, and it equates to 6.02 times 10 to the 23 moles. Now, it is supplied to you. You do not have to memorize this number. So part of that all-important data booklet that you're provided with in all examinations at AES Chemistry. So don't panic about memorizing it. But getting your head around what it actually represents is quite core to the mathematical skills, especially in Unit 1. So you can see that you've got 10 grams of sodium. Well, if you simply apply that first principle of mass divided by AR, then we know it would be 10 divided by 23. You get that mass in the data sheet. It is probably worth me mentioning just briefly that don't forget that the masses of atoms is a lot more precise in AS than A2. Please use the one that you are supplied with. Some of you are pretty good at memorizing your masses from GCSE, but they have been adapted somewhat when it comes to certain elements. Things like magnesium is recognized as 24.3. Not simply 24 anymore. You can see there, then once you've worked out the number of moles, you simply multiply it by Avogadro's constant, and that would equate to giving you the answer 2.62 times 10 to the 23. Now, that is fine for an element, as sodium, as is the case for magnesium there. So same approach, you divide it by the atomic mass, but as I said, 24.3 for AS chemistry. It is a bit more precise. And then you multiply by Avogadro's constant again. Now, take a break and read questions carefully at times, because sometimes it is a bit of a temptation to rush in, of course. But if you look at the last one there, it says 5 grams of methane, CH4. First part you'd expect to do as normal. So you can see there that there would be 1.88 times 10 to the 23 molecules of methane. However, when you look at what the question is actually asking you there, it's asking you how many atoms there are. Now, there are 5 atoms in methane, of course, 1 carbon and 4 hydrogens. So it is all important that you then take that final step in this calculation and multiply it by 5 to get the actual answer to what the question was actually being asked. So how many atoms are present in that 5 grams of methane, of course. So when we look at 1.3, which is what I'm going to base the rest of this presentation on, you come across quite a lot of those gas laws and the calculations that relate to that work, of course. So ideal gas equation is actually specified as one of the learning outcomes. So it's something that hopefully by this point you're all familiar with, but maybe not confident in its application and use of on a regular basis. So I'm going to work through how you'd approach such questions and the kind of pitfalls that lots of you may fall into. Because as I said earlier, there are quite a lot of pitfalls that you can fall into, and they're common across the entire cohort that we see of pupils that attempt AS and A2 papers. So this, if nothing else, you learn how to avoid those pitfalls, hopefully. So hopefully you'll be able to recall the ideal gas equation, because it is specified and it is expected, therefore, for you to be able to memorize it. It won't necessarily be given to you. And in fact, the majority of questions, it's not specified as part of what is expected to be memorized. You need to be able to recognize, convert the standard units there appropriately. And you need to be able to use that ideal gas equation then to confidently carry out the appropriate calculations. So gas volumes, as you are familiar with, the volume of any given gas is not fixed. It changes with pressure and temperature, of course. You should appreciate that if the volume of a gas expands, then the pressure internally of that gas therefore decreases. And you will be hopefully able to recall specific laws that you may not recognize the names of, so Charles and Boyle's law, etc., but you'll hopefully be able to appreciate the relationship and how they are directly and at times inversely proportional to each other. So the ideal gas equation allows you to calculate the number of moles in a certain volume at any given temperature and pressure. So as you see there, it equates to PV is equal to nRT. And as I mentioned earlier, it is something that you must be able to recall from memory and not assume it will be supplied to you. So breaking down what all of these letters stand for. So pressure. It is important, however, that pressure for the use of this ideal gas equation is given in pascals. So atmospheres is not good enough. It is important that it is represented as pascals. The volume, again, something that you're not overly familiar with, is expected to be specified as meter cubed. So you're familiar with centimeters cubed and decimeters cubed from your GCSE, but conversion then and scaling it up to a meter cubed is something that is essential when you approach the use of PV and RT. The number of moles, we've done that already in this session. R stands for the ideal gas constant. Now that, again, is something that's given to you in the data booklet at the beginning of all exams. So it is something that you're not expected to recall as a value, but you do need to recognize what its significance is. And then temperature, as is the case for the entire calculations for the ideal gas equation, the combined gas laws, etc. You must remember to convert it into Kelvin. So these equations are only true and will only be functional when you convert a temperature to Kelvin. So converting units, whilst we're on it, it is highly important that you build up some confidence in conversions. So it says there that you've got 1 bar, something you're probably not overly familiar with dealing with. 100 kilopascals indeed converts into 100,000 pascals. As I said, the PV-nRT works on a meter cubed, so you have to recognise that is 1,000 decimeters cubed, and equates to 1,000,000 centimeters cubed, etc. The conversion of temperatures there, so absolute zero converts into 273, absolute zero when you convert it into degrees C. So 0 degrees C is 273 Kelvin. 20, which is something that does sometimes creep into questions, is recognized as being 293 Kelvin, but very commonly used is that use of 25 degrees C, which is 298 Kelvin, of course. So don't forget the converting unit is essential. And as I mentioned earlier, it is in fact one of those very, very common pitfalls that pupils fall into. And it is one of the main sources of loss of marks. Okay, so one of the common errors that leads to you losing what ultimately could be quite easy marks. So that is just the section from the start of the data booklet that you will be supplied with. As it says there, you can see that it converts or attempts to help you convert quite a lot of the values. So you've got the kilo, you've got the mega, giga, etc. Just look at what it's actually giving you, okay? And then multiply or divide accordingly. So the ideal gas equation there. So just typical kind of question that might come up, and I've tried to make the first one as easy as possible, so I've stuck to the standard units that are required for the PV-nRT. So it says that how many moles are there in 0.06 meters cubed of hydrogen gas at 283 Kelvin and 50,000 pascals. So first, convert units to the correct form. In this case, there isn't, it's the data supplied, so you can use them as given. Okay, the volume is already in the meter cubed, which is what the required unit for volume is, and then the temperature is 283 Kelvin. Okay, what you'll very, very often notice that they'll give you temperatures in degrees C, and it is up to you to convert it accordingly before you attempt anything else. So if you look at the question, this is asking you how many moles, so we need to therefore isolate the unknown value, because obviously there'll only ever be one unknown in an equation, otherwise it makes it not possible. So you've got here PV equal to nRT, rearranging it to n on its own to make n the subject therefore of that equation. And then it's just a case of inputting the data as required. So you can see there it equates to 1.28 moles. Don't forget, another source of error or loss of marks then is just not putting in the units at the end. And that is again something that you can hopefully after this session avoid doing, because it's something I would probably say is a bit of a throwaway mark when you just forget to put the units in. So another question here does require some conversion in this case. You'll notice it's asking you what volume does 2 moles of argon gas occupy at 27 degrees C and at 100 kilopascals. So look out for that K, it makes a whole world of difference. So conversion here, N is given, so it's just 2. The temperature there is given initially is 27 degrees C, so converted to Kelvin, it converts to 300. The pressure, this is again is something that lots of people miss, is they see the pascals and then they kind of relax a bit and think there's no conversion required, but it says kilopascals. You must then scale up by a factor of 1,000 because kilo is 1,000 times larger. So it's not 100, it's 100,000 pascals. Rearranging to make, in this case, volume the subject of the equation. So V is equal to nRT over P. And once you are confident that you've done step 1 and 2, then step 3 is just a matter of putting it into your calculator. Now, be careful that you're using a calculator with confidence. Be careful that you understand when brackets are appropriate, when to press equals before doing something else, because all calculators, especially the scientific high-tech ones, are actually geared to work off the BODMAS law. So it'd be a real shame if you don't get the correct answer because you aren't familiar with the workings of your own calculator, really. So that'll come with practice, and you'll come to know how your own personal one works, because there are slight tweaks here and there that differ from calculator brand to calculator brand. In this case, the volume would have worked out to be 0.0499 meter cubed. It is more than acceptable to leave it in meters cubed, but you are welcome also to convert it into something more familiar to yourself. If preferred, you can convert it to decimeters cubed if that is something you would like. It's entirely up to you. So the ideal gas equation there. There's another question. Here, it's just a case of they sometimes add on the fact that it would be what we call a builder question. So you can see there, it asks that a temperature of 60 degrees C and a pressure of 250 kilopascals, a volatile gas occupied a volume of 1,100 centimeters cubed and had a mass of 1.6 grams. What is the relative mass? So this is kind of working backwards from the two I previously showed you earlier. So initially, you'd work out the N, or make N the subject of the equation, and putting in all that information, it would equate to 0.0994. And then it would be another rearrangement required here, which is that you'd rearrange it to get the number of moles is equal to the mass divided by the molar mass. So in this case, the molar mass works out to be 61 grams per mole. So that is the ideal gas equation. I've given you another question there. You're more than welcome to pause at this point and then attempt it and then check your own understanding, because that is just kind of a question that just encapsulates a few of the points I've made over the last few minutes. But moving on, the question is there. It is taking into consideration here the stoichiometric ratio. So you can see that we've got 2 moles of the nitromethane producing 2 moles of carbon dioxide, 3 moles of water, steam or gaseous form, and then 1 mole of nitrogen. But if you look at the stoichiometric ratio, don't forget it is the lowest ratio possible. So because the question is asking you about 1 mole, look about what the relationship would be then with the other products. So 1 mole would produce 1 mole of CO2, would produce 1.5 mole of steam and half a mole of nitrogen. So overall, what you need to be looking at then is the fact that 1 mole of the reagent produces 3 moles of gaseous product. So when you put that into the question then and rearranging it to make V the subject, you would end up having 7.43 times 10 to the minus 2 meters cubed. And that therefore requires you to scale up according to the stoichiometric ratio. So go back there quickly just to point out that that's where the root of that 3 is, because you would get 3 times as many moles of the gaseous products. So just to move on, it might not be as clear cut, or it might certainly not be what you've been taught or the way you've been taught, because the next few points and the next few slides covers laws that aren't specified specifically anymore. And it leads up to the formation of what I call the combined gas equation. So Boyle's law was something that was a long time ago, because I'm not as young as I was. So the Boyle's law was specified as something that you needed to recall, and it links the pressure and the volume of a gas at a constant temperature. So it says there that at a fixed temperature and a fixed mass of a gas would have the inverse relationship between the pressure and the volume. So if one goes up, the other one goes down. Okay, so the Boyle's law as specified that will lead into my combined gas law there is that P1V1 is equal to P2V2. So the total pressure multiplied by the volume is consistent, therefore, throughout an equation. Okay. Charles' law then was another one that was specified. It just takes you through the link between temperature and volume of a gas. So the pressure remains constant, which is the assumption there. Then the higher the temperature, the larger the volume. Okay, so mathematically then, the temperature is proportional to the volume. So if I then move on to the last one, it isn't a specified or named law per se, but what we have then is Bohr's law, Charles' law, and then the pressure law, which is that the pressure of a fixed mass is directly proportional to its absolute temperature. You can then put all of them together to form what is called the combined gas equation, which equates to P1V1 over T1 is equal to P2V2 over T2. So you take the initial pressure, volume, and temperature, and if you are then supplied with a new pressure and a new volume or a new temperature, don't forget only one of them can be unknown at any point, then it allows you therefore to rearrange it to get a new value or calculate a new value. Okay, this is what, and I may be going across what you've been taught by your teachers, of course, but this is something that I personally encourage my pupils to use if they feel confident in doing so, because it works on any appropriate unit. So unlike the PV-nRT, which is insistent on having pascals as a pressure, insist on having a volume in meters cubed, the combined gas equation allows you to use any appropriate unit as long as you consistently apply it. So as long as you are using decimeters cubed, you can use decimeters cubed throughout. As long as you are given a pressure in atmospheres, you can use atmospheres in both cases. It makes no difference. The only exception to that, of course, is that last point there. Temperature, as I mentioned very early on in this presentation, always has to be in Kelvin. That is not negotiable at any point. So you must convert your temperatures to Kelvin to make any of these laws and any of these equations work. So here's one example. I'm going to take you through three. Again, you're welcome to stop and pause and try them yourself, but I'm going to go through the solutions as quickly as I can. But I would suggest that if you're confident, stop and see yourself whether you've got the idea. So as it says here, you've got a fixed mass of a gas at a constant temperature, has a volume of 500 centimeters cubed and a pressure of 1 atmosphere. So I've already gone against the units of volume and units of pressure, but it doesn't matter because it will work, okay? It says there, what will the volume be at a pressure of 4 atmospheres, therefore? So as the temperature is constant, we can use simply the Bohr's law, if you can recall Bohr's law on its own, or alternatively, you can use a simplified version of the combined gas law. So the combined gas law there, we are told that the volume is what is being asked of, but it does also state a constant temperature. So we could just scrap out those temperatures, and it simplifies, as I said earlier, to what is recognized as Boyle's law. P1V1 is equal to P2V2. So once you've got the equation simplified to your liking, then it's simply then inputting the data as appropriate. So it says there you've got P1V1 over P2, because I've made V2 the subject of the equation by rearrangement. It equates to 125 centimeters cubed. It doesn't specify it, okay, but because you were initially given the volume in the questions 500 centimeters cubed, it is probably advisable to then give your answer to centimeters cubed as well. Unless it is a hugely massive number or a very, very small number, it is probably unwise to deviate away from the specified units they've given you. Okay. The second example there, a gas has a volume of 1 decimeter cubed at a pressure of 1 atmosphere. At what pressure will it occupy 100 centimeters cubed of gas? It is a bit of a tricky one in this case because they have given you 2 different volumes. Do not, units of volume. Don't let that throw you. It is easily converted. So the temperature is constant, so you can use Bohr's law. But in this case, you have to convert one of them into the other's unit. So either convert the 1 decimeters into centimeters cubed, or vice versa, convert the centimeters cubed into decimeters cubed. So for this one, we'll choose to convert to decimeters cubed consistently, which takes that 100 centimeters cubed, therefore, to 0.1. Okay, so making P2 the subject of the equation, we've got 1 times 1 divided by 0.1, giving you a final pressure of 10 atmospheres. Atmospheres, as I said, is the units that need to be specified. It's given the question, and it is a common error that pupils forget to give an appropriate unit at the end. The final example I'm going to take you through here then is one that requires the entire combination of the laws as given earlier. So the pressure of a gas at 27 degrees C is 150 kilopascals. Assuming volume is constant, what will the temperature be at 180 kilopascals? Okay, so lots of things to keep an eye out here. Okay, it is 27 degrees C, so I will have to convert that, but there is no need to convert that kilopascals into pascals because it works regardless as long as you are consistently using the same units for the pressure on both sides and the volume at both sides. Okay, so there's no need to convert that 150 and 180, stick with it. Okay. So the volume is constant this time, so we use the combined gas equation simplified again. So we can scrap out the volume in this case because it's specified as being constant. So it simplifies then to P1 over T1 is equal to P2 over T2. So with a bit of rearrangement then, but remembering to convert that 27 degrees C into Kelvin. So 27 plus 273, which is obviously the conversion required, takes you to 300. Rearranging to get the subject to be the second temperature, T2. It is then just a case of putting in 180, no need to convert, times 300 divided by 150, taking you to 360 Kelvin. Okay. Now, initially, the temperature given to you in the question was in fact degrees C. And for that reason, I would suggest you then make that little bit of an effort as a final step to convert it into degrees C yourself. Okay, so more practice is required. Well, practice does make perfect, okay, but there is plenty of resources out there. Naming just one then, I would suggest that if you want to build your confidence even further, get on to that WJC question bank, which is a resource available to all of you. There are plenty of past papers out there as well, but if I point you in the direction of the question bank, that is a bit more specific, and you can put in just the criteria of the ideal gas law, etc., and bring up just the questions that will help you practice that particular skill at that time. Okay, it goes without saying this is only one topic. It is one of many subjects that we've now covered over the recent years when it comes to AS. As well as GCSE and A2 chemistry, of course. But if you want access to other videos, then obviously the link there will take you directly back to the Carlam Cymru homepage. And hopefully you found this video useful. And if not, or you have any further questions that need more clarity, then please either contact your own teacher or, if required, contact Carlam Cymru. So I wish you luck whenever you take on those exams, but hopefully this helped you. Goodbye.